It's my camera and see. Yeah, it is showing which camera is it.
Oh,
Which camera is this? It is our camera, right? Yes, check it.
yeah. Absolutely.
Yeah, it is.
Okay. Do I need?
Yeah, you need a host key.
So you're a host key.
Yeah,
Oh, then you're the participants, I guess. No. Just keep participant to see. Now claim host and put your secret number between 6 and 10 digits. And I'll be right back, okay?
Okay, okay.
Okay. So your
Oh,
secret
it's not straight, huh?
thing is not.
You're tall.
Do you need help or?
I think it is okay, right?
I think
What do you
so.
think? Maybe a little down.
Oh, we don't, well, participants, we can wait with closing participants just to see whether,
What?
do you cover the whole blackboard? Maybe
I'm
turn
going to
slightly that direction. No, this direction.
Better? More?
Yes, now, right? But we don't need that
Yeah.
yellow thing.
Is this straight? Okay, checking.
It is straight.
Yeah.
And let me see if. I know.
Oh, let's go.
Hi, how are you? Right. Sorry, I did not have any more suggestion.
Oh, no, you guys are the best. I appreciate it. I found somebody who's doing math like mine.
Huh,
Finally, it's been.
Carbondale?
No, he's the co-founder of the OEIS. Do you know what that is?
What?
OEIS. It's the online
Yeah. I can't
encyclopedia
get into C
of
special.
integer
That's correct.
sequences.
Oh,
Starting from S, right? His name starts from S.
Yes, Simon Plow. Yeah, that guy.
Oh, fantastic.
Yeah, I finally found somebody and he like, wow. So yeah. So there might be good things coming for me.
yeah.
I gotta reach out to him still. I've been very busy lately. So yes. No, I appreciate your suggestions very much.
Yeah. Maybe you want to still talk to Dr. Boo?
Yes, indeed, yeah, Yeah, I just need, because he does education.
Yes,
right?
he does education.
So I must change my angle a little bit
Yeah.
for teaching, right?
Yeah.
Because I had my wife, her 14-year-old daughter. I was telling her about my math over the phone, and she was doing it.
She must be smart because I cannot do. You tell me.
No, what he's saying, I think, is that we have been brainwashed so much.
Oh, yeah,
We
yeah.
don't understand.
Thank you so much. You're amazing.
Kids are.
Did you try again?
Are you still using AI? You know, AI is awesome actually. I don't know why people don't like it. It's a good tool, just like a car or a computer or phone.
You know, I noticed that I just put some of my homework, on the from calculus. Immediately, the answer over there with explanation of steps and everything.
Oh, yeah.
Because giving homework doesn't make sense anymore.
Yeah, exactly.
I mean, it does make sense, but collecting it doesn't make sense. Just do it, make sure you know how to do it. If you want to use that thing in order to improve yourself, but the thing is you and you know how to do it.
So when you give exam, you maybe go, oh, this is AI.
What are those glasses? now?
Yes,
You're-
exactly.
I think the coffee is ready. Hey, hello, hello. Right, in 10 minutes, but coffee, right, that's.
So why not? I mean, how much this was a function for?
This
Probably-
one has a lot of iron in it.
I like iron. Iron?
Iron.
No, iron's okay. Lead will be okay. But this is French. So, other.
There is a little bit English thing
Yeah.
that is due to.
Oh, really?
Right now, it's not about habit,
Or
yeah.
something?
I
Probably
think
should learn mathematics.
literature thing. A lot.
Well, we get a degree here.
But this is not dangerous.
I don't know.
Older than-
Oh, thank you.
But does it, do we consume the iron? No.
Personal edition.
So it doesn't leak into the. But lead would, right?
That is bad.
Okay, it's not bad.
And
The problem is like, unless you were a student, it was like $5,000.
yeah,
So it doesn't help with iron deficiency.
and it's.
But iron deficiency, in India,
Good is what I-
everybody made food and
Right.
iron.
It's not like.
Now people are
Plastic.
plastic and aluminum. That's really bad.
That one is bad, right?
Aluminum is also.
It's really bad. Does it leak?
Yeah. It is linked with Alzheimer's disease.
Yeah.
Although I see papers,
But some people claim that this is not the
Complex analysis.
presence of aluminum in your brain because it's this is just a result of other.
could be people do not know.
Whenever you make
I know what they
turns,
wrote it.
branch cut decisions, it's often wrong.
But are there people who cook in iron?
It's our interest.
Yes.
Numerically, it's.
What about
No,
steel?
long.
Steel is iron,
Yeah, I
Mostly
know, but
iron.
steel is
So it
iron
doesn't have to do much.
and.
chromium and carbon.
Carbon is also.
Oh, there's a lot of carbon in
Scared
it.
to try it.
Does cooking in an iron pot
You
give us
basically have
sufficient iron to?
If you cook every
It's 1
time,
minute.
yes, it's
Yeah.
much better than without.
Oh, and I have a request.
Yeah.
In about, I don't know, maybe like 7 minutes.
One
We'll make
is
a
iron
minute
that
break.
comes from
So
the
people can grab coffee because it is it okay?
Of course,
those are the
otherwise
one
no
that
one's
is
gonna
little bit rusty.
Listen
last through my
for
class.
the
Now
whole
you're
exam.
asleep.
Yeah.
So it can be, what do you
Then
think?
you know what you're doing, everything gets better.
Whenever, you just let me know.
Not only that, I
Fine,
mean,
yeah.
people are-
I'll just
It's,
wait.
it's the review definition
Is the
before.
Yeah.
No, iron pill is just.
Just explain.
You have an airplane, maybe?
Surgery.
My mom's
Actually, I do. I have it.
Yeah.
Medical
It's
plan.
why you're going
Normal
up.
to it.
Everything
Well,
about
you would
I'm
measure it. The second one
Only
was
one is
start
to
by
go
one.
outside to do some, because I.
When I was doing everything was
Many
iron.
times
Even
measured.
out of the
Last
last
time you did this,
Dogs
I
were
mean,
barking
Done.
for 2 miles with.
Right. Demands. Do you think something goes into the food?
Oh, yeah.
Of course. I think you
It
should.
doesn't have to be.
Yeah.
Yeah.
If you
Well,
eat it,
Yeah.
it's much better.
Nice.
Yeah.
Oh,
We can take one better. in
I was
the
thinking
digest.
of that too.
Not only that,
By the
when
way- by
iron
the way,
goes in your stomach, it's going to
Do
be
you think like
solubilized
draft or
because
do you
of
need
the acidity.
I don't think so.
Oh, you
I
not?
was gonna
There's a
try
lot
to
of
finish
HCl
today,
there.
Okay.
It's gonna
But you
be
don't know,
solid.
right? I
Yeah.
mean, it might.
So as long as it's.
I just want to know.
Just to, so really, it's like whatever you need. I don't want to like hog all the time, you know?
Yeah, no, okay.
So
As long
I was
as-
gonna try to
It's
finish
the
today so that
bioavailability.
people could have a chance to share.
Okay, let's see.
Yeah.
Too much is not good.
So, okay, so ladies and gentlemen, welcome back. And today will be the second part of the talk Matthew provided us with.
Yeah.
And in about 7 minutes, we'll have a break. Just 1 minute break to get coffee. Okay? Because right now it's still brewing. Okay, so
All right.
thank you. Let's
So-
go.
We're asking this question last time, which finite measures on Rn satisfy the following? So for every direction, there is a hyperplane with that direction as its normal vector, about which the measure is symmetric. So in other words, I take a hyperplane here for every set A, I reflect it about hyperplane, the measure remains the same. And a similar question for spheres. So for every point of Rn, there's a suitable radius such that the measure is symmetric about the sphere with this center and this radius. So let's say this is the sphere with center x0 and radius lambda. Right. There's some set A. I reflect it. So this map we called it. I'll give you the formula for this, right? But this is the reflection or the inversion of A, and I want to make sure that these sets always have the same measure, right? So this is for every A, this happens. That's what it means to be symmetric about the sphere. And then for every A, this happens is what it means to be symmetric about the hyperplane, right? So let's remind ourselves. What do I want to say? So these reflections, right? So remember, if I give you a hyperplane, reflection about that hyperplane is a map on Rn to Rn. Reflects about the hyperplane. That map lifts to functions, right? So the action of reflection about a particular hyperplane is just defined by a composition. So reflection by H of F at X says first reflect H, reflect X about H and then apply F, right? So if this is X and I want to apply this map to X, first I reflect it to get this guy and then I just apply the original F, right? And we'll have a similar action, slightly more complicated for this thing. So if I invert, so the action of inversion about S is defined, so I'll have a similar thing. So yes, but I have to adjust it, and I'll show you why today this adjustment is necessary. So I have to adjust it. So this S, let me not denote the center and the radius, but it's center x0 and radius lambda. So this factor depends on that. So it's a little more complicated, right? It says if I want to evaluate, say I have a point X, if I want to evaluate this map at X, first I invert X. Evaluate the original F at the inversion, and then I have to modify it by this thing. And so I'll show you that in a moment. So we discussed those actions last time. Let me remind also, if I have a function taking non-negative values, it induces a measure. So so if I have a non-negative value function, it induces a measure, which I'm going to subscript by f, and the size of a set A is just integrate f over A. I'm gonna actually today I'll get in the habit of writing the input variable or the dummy variable. So here's the picture, right? So and this is the graph of f, and say this set is A down here, and shaded region is the measure of A according to f, right? If you're a measure theorist, some folks would call this the Radon-Nikodym derivative of mu. If you're a probabilist, someone would call this the probability density function after suitable normalization. If you're a, I don't know, chemist, the way you should think of this is this is some piece of mass, and this function tells you that where the function is large, it's very dense. And where the function is small, the mass is sparse. Yeah. Okay. So what we want to do is, if we're going to answer this kind of a question, I need to understand how, if I start with f, how does this measure compare to the corresponding measure if I put reflection by h of f here instead, or if I put inversion of f here, right? So I'll show you that these actions are defined. So these guys are defined. So that if I want to measure with f a reflected set, it's the same as reflecting f and then measuring the original set. That one's easy to draw. I'll draw that for you in a second. And then this one's also defined in this way to give you the analogous property. So I'm going to draw this one for you because I think this is maybe obvious. I'm going to compute this one for you because I want you to see exactly where this thing, like why this thing is there, right? So, and this one's just too hard to draw unless f is a very particular function, like 0 maybe, or 1. So let's do this one, right? So for this one, here's the picture, right? So this is Rn, I'm drawing it as if it were a line. Let's draw f. So here's f. And let's say, so in this diagram, my hyperplane H has to be just a point. So I'm going to draw it here. So if I reflect f, here's how it looks. So this dotted line is not part of the picture. It's just so that I can hopefully have some chance of drawing this with some level of accuracy. Right, so it just reflects f, right? And so this one, it says this says if I have, so let's look at a set A. This if I measure A with the reflected f, so that would be like this region here. It's the same as reflecting A and then measure it with the original F. Right, so this picture is a watertight proof, I think, right? Let me show you. So are there any questions on what's happening there?
Okay. So, can you just repeat for me at least, and maybe
Mhm.
everybody, what you want really, this quantifiers, that.
Yeah.
That for every F, you want to have at least one plane where the thing is symmetric.
No, for every direction.
For every direction.
Every
right?
direction, right? So a hyperplane comes with a
Right, yeah,
direction that
that's
tells you like how it's oriented.
But where it is.
I don't care where it's oriented,
Okay.
right? So for every
So-
direction, right? So say I choose this direction, I move the hyperplane parallel until the measure is symmetric about that hyperplane, right?
And
But this has to happen for every direction. So if I choose this as my hyperplane direction, I move it parallel until the measure is symmetric about also that hyperplane. Right? No matter which direction I pick, I have to be able to choose a hyperplane with that direction about which the measure would be symmetric.
And the second part, maybe after you give an example, or you can answer now.
So if you want to just know the quantifiers, what this says is that for every center
Mhm.
of a sphere, I can find a suitable radius about which the measure is inversion symmetric.
Sounds difficult to be satisfied, right?
I'll give you
Now
some
with the-
examples.
With the scaling factor, makes it easier to satisfy.
I would say that's accurate. Yeah.
Okay, oh, I
That's why
see.
it's there.
Oh, you say-
Yeah.
Impossible.
Yeah. Well, it's there so that you have this. Let me do the computation. You'll see it has to be there. That's the only way that
Yeah, something has
the
to be
gods would allow it.
Yeah, so is the lowercase n for the number you're using, is that the number of directions being considered?
the dimension.
Number
Oh,
Yeah.
n is in Rn, right? So
Okay,
Right
Rn,
here, yeah.
so Rn is the set of n tuples. Okay, so R2 would be like the XY plane.
Yeah, and belonging to the sphere is not essential, right? Just any vector E. Long or short.
Yeah, but I think, I don't know, I've been
You don't-
brainwashed to always normalize the direction vectors. Yeah,
Okay,
as long as they're not zero.
you just
right?
obey.
Yeah, I just obey, yeah, yeah. Just like I was taught. Okay, so,
Oh, maybe this is the moment people can grab coffee and about.
oh yeah, please.
Nobody?
I grabbed some before I came in, you see, while it was still making.
I'll pause.
You don't?
Yeah, yo, please, go get coffee.
Oh, hey, hello.
So to me, sort of, it sounds like you decided the answer to those two questions, or this one question is no. So we're gonna change the problem slightly.
No, so the that's not a yes or no question, right? The question is which measure.
No is in
satisfy this?
none,
Right.
unless you suitably change what you mean. Right? This
Let
trick
me
with the
do the
reflection makes it
computation.
look like-
I think it's gonna answer your question, right?
Okay,
So let's look at this, right? I have to, before I do this computation, I have to give you this inversion formula. So let me remind you of this inversion formula. So recall. Right, so again, S is, I'm assuming center is x0 and the radius is lambda. Right, so that's the inversion of X. So here's an X, but let me draw another one. So here's X. The inversion is going to be along the same line that contains the center of the sphere and X. But points inside go outside, right?
And it doesn't depend on the dimension n?
No,
No, okay,
no.
okay.
Okay, so let's look at this, right? If I do,
why would it in some particular frame, like it's just 2 dimensions? Exactly the one the chalkboard's in fact, like euro X.
You
Your
know,
line
it's an
direction.
n dimension, that's why I said dimensional sphere. In RS,
That's not where this is going.
but anyway,
But I need you points to find one, so.
I wanna measure. This is the measure. According to F. Of the inversion of A. Right, so let's, where's this formula? Right, the function that I'm using to measure here. Is F, because that's the integrand. But the set that I'm measuring over there is not A, it's the inversion of A, right? So let's draw a picture so that you can see why I'm choosing to do what I'm choosing to do. So. I'm gonna draw it actually over here, right? So over there, X is in here. It's in the inversion, so I'm gonna realize X. As the image of some Y in here. Right, so I change variables, I don't need this, so. Right, with this formula, right, so X is one of these, dx. So this thing, I'm asking you to just believe me, that's the Jacobian. Anyone try to compute this Jacobian while we're gone?
Yeah, that was your homework for us, right?
Yeah, try it. Alright, so we do this, right? The new integration domain is of course A. This f of x becomes f of inversion of y. And then this Jacobian. That. And so you can see that this is exactly, where's my action? It's exactly this, right? So this is. Right. So then this is the same as using this function. To measure the original set A, right? So again, the actions, these two actions are just rigged so that I have this, right? The measuring a inverted set with a function is the same as measuring the original set with the inverted function. Right? Similarly with reflected, right? Okay. Maybe we should look at some examples. By that I mean, we should look at some examples. So I'm gonna consider so this measure, right? So for this measure, I think this one is probably clear. Right? I think no matter which direction I choose, every hyperplane with that direction works. Let's look at this. So if I fix an x0, can I choose a lambda such that this measure is symmetric, right? So let me let x0 in. And I want to know, is there, let's find lambda, and let me emphasize that the point is the radius here is allowed to depend on the center, right? So find lambda positive such that mu1 is my function. A is the same as mu1 theta S of A. For all A, right? We just do the computation, right? So I have the formula for this. Right? Let's look at this, right? So we know using this over here, that if I do mu1 so that's like this, but f is 1. It's the same as inverting the function and measuring A, right? So if I want this equality to hold, maybe it's easier to compare these two because at least they're both measuring the same set. Right? So let's write this down. Want. So mu1 of A, which is to be mu theta S of 1 of A. And I think I erased my action. Let me write the action up here.
Yeah, we still have the Jacobian.
Yeah.
Oh, yeah, okay, good. Yeah. Oh, good. Yeah, so this is my action, right? Theta S of F is this guy, but F is 1, right? So only this piece arises, right? So the question is, which lambda makes that equality hold? It's allowed to depend on x0.
Like pull it out of the integral.
X minus X, right?
Yeah, so this should be
Lambda should
What happened
depend
here?
upon x,
Yeah.
of course.
On x0.
it can depend on x0, but it shouldn't depend on x.
Yeah.
So let's see.
A is just a set. He didn't draw a picture of it. Well, it can be any set. That's what I'm gonna ask him.
Yeah, that's the
That
problem.
is independent of X naught,
Yeah.
right?
I think perhaps this is not a good example.
Let's just suppose it doesn't contain x naught. And see if your example works, or at least that. If you gotta.
I think
we
we shouldn't, so I kind of went out on a limb too far anyway. Here's why.
One doesn't work.
This isn't a finite measure anyway, right? I thought I had an easy example, so I'm just gonna jump to the.
Could you choose F to be 1 up to 2 miles from the center and then 0 outside? Would be
Oh,
nice.
tricky.
I mean, you could do whatever you want.
No, that's what I mean. Will it make your example easier?
So let's see.
So there would be a density.
So this has to hold for every A. So once we choose F to be 1 somewhere and then something else somewhere else, I just choose A to like grab all of like some of that information here and some of that information there. Like this is supposed to happen for every A, right?
Yeah.
So would this question be equivalent to in physics? They say that if the universe is symmetric about every point, spherically symmetric about every point, what is the metric of the universe? Is that the same question?
It might be, but spherically symmetric,
About
every point has a radius about which the universe is spherically symmetric. It's not every point and every radius. Every point has a radius, and the size of that radius depends on the point about which the universe is spherically symmetric. Maybe is how the physicists say it. I don't know.
No, in physics, the inversion, the symmetry,
Mhm.
the inverted symmetry, let's say, is typically applied to Maxwell equations, where they show that they are invariant under inversion through any point. So I'm waiting.
So
maybe
If you do the
somehow
bare
show
maths,
Those are
you can
Well,
get-
I think of other.
differential equations, right?
Yeah.
Yeah.
So we'll get to kind of the application of this property to differential equations today, hopefully.
Okay.
So you need to look at a finite measure.
Yeah, so
So-
anyway, let's
You
Let's
can
kind
have, you can have point measure, something just comes all the way to one point.
so why does
That's
that not
interesting.
work? So why does
You mean like Dirac?
Yeah, just something is one place, yeah.
why does that fail is because
Does it
I
satisfy
can, I
one?
can choose, let me call this something else, right? Centered at Z, right?
Yeah,
So if I choose the center x0 to coincide with Z, then when I invert, all the mass gets flipped out to infinity.
yeah,
Right.
okay,
So I
okay,
don't want that.
okay,
Yeah.
okay, so that's a good example then,
Yeah.
right? Another thing would be like a Gaussian.
Kind of. So I'm gonna give you. I think the Gaussian is the right idea, but let's look at the one that.
You can still do in one dimension. One dimensional case
What do you mean?
for Gaussian. But it
I
doesn't.
could. I just want to give you the one that works, though.
Yeah,
Yeah,
I think it's.
yeah, we want one
spirit.
example that works, yeah.
Yeah.
Question is, what are all the functions with this property, so we're trying to find one.
So there's a computation here. I'm going to hide the details from you because you don't want to see it. But let me just give you the answer.
But don't hide the truth.
We shall take it on faith from now.
You'll believe me.
Gaussian.
You know, this is,
The Gaussian is.
yeah, I know. You know, it is, the graph looks kind of like a Gaussian to us, but it's got different properties. In terms of the job.
So this is a direct computation that I'm about to do. About to show you the result of. So let's look at this piece, right? This is just a polynomial, right? I'm just
Yeah, sure.
taking the 1/n power and then flipping this guy up to the denominator, right? And then if I invert this thing, it's a polynomial. So this is like, you can compute this directly. It's just a matter of like arranging terms. It's just not a fun computation. So let me factor everything nicely. Here's what you get. Right, so this holds for every lambda, for every x0 and every x. So what you can see, who cares about this? That tells you right there, so. So if I choose x0. And then I choose lambda to kill this chunk. Then U and his inversion will be symmetric about this thing. Right? So here's a family, it's not a family of functions yet, but here is a function that does it.
Then you could choose another lambda that kills the first term, right?
Yeah, but this one depends on x, right? This is why I stopped.
Right,
This is
okay,
why I
okay.
stopped.
Got
this
it,
example, yeah.
Thanks,
So I
yeah,
want this one to depend only on the center point.
right.
Yeah. Good, so we have an example. So what about, so that does this, right? For that U, what about this? So we saw last time that this U is radially symmetric, right? If I were to draw this, here's the origin. Here's U, right? So we saw last time that if I have a radially symmetric function, then this always works, right? Remember, I drew a contour map to illustrate this. So this works for U as well, right? So U does this, right? What are the other functions, right? So I guess technically speaking, right? The measure induced by U is what I'm talking about. Does this, right? How do I know this is a finite measure? So let me say no.
Okay.
No expected value. I think this is the famous week of Agnesi, the curve for in one dimension. This is just generalization, and we always do it, right? The integral is something pi or pi
Let me
over
say. Right, so I want to make sure that the measure is finite. So if I integrate it over all of Rn, I want something that's finite. How can you tell? The decay is like 2 to the sorry, x to the minus 2n at infinity, and it's bounded above, right? So there we go. So it's finite. It does it. It works, right? This is everything. So you can get some cheap you can get some extra cheap examples just by translating this guy and dilating him and scaling him. So more examples. Let me say translates dilations and let me say non-negative constant multiples of u. So for example, let me call it. Let's just say C u of r x minus c. I'm gonna move some space here. So this is C. Yeah. Right, so I put in x minus z, I'm just putting x, like shifting the center away from 0 to be centered at z. If I scale the input by r, then I should pick up an r squared here. Right now this is a 1, but I'm going to change it momentarily. And if I scale the whole thing on the outside, I get this, right? So typically my dilations, I like to do it like this. So if I'm going to multiply by a constant here, I might as well do it so that at least this dilation piece is preserves the whole measure of Rn. It's very independent of R, for example. So this is the only thing that changes the measure. Right. You can check if I integrate this thing over Rn with R and Z, it's the same as integrating this thing over Rn with R equals 1 and Z equals 0. Right? It's just simple change a variable, right? Okay. Theorem. Maybe 1996 is my estimate for this one. So if mu, so if mu is induced by a measure, by a function that is C1, satisfies 2, then mu has to be of this form. Or another, sorry, f has to be of this form. So mu has to be mu f with f of that form, right? I'm gonna give this family of function a name. There's no reason at all for me to name these bubbles. There is, but I'm just not gonna get into it at all.
Too embarrassing, huh?
That's too embarrassing.
What happens in Rio Station?
Something like that, yeah. Then that so the story is then f is a right. Or in other words, mu is induced by a bubble, right? theorem. So this is Yan Li and Meijun Zhu. Meijun was my postdoc advisor. Yan was his advisor, and Yan was also the advisor of my advisor. So Yan weakened this assumption here to C0. So let me say
zero. Continuous.
Oh, I see.
And C1 means differential your points.
oh yeah, I guess I should say this, right? This means that f has one derivative and that derivative is continuous. This means that f has zero derivatives, but f itself is continuous.
Just means F is continuous.
It means f is continuous.
Yeah.
Yeah. But why the zero, right?
Yes.
Zero derivatives, right? Okay, so these theorems are theorems about measures that happen to be induced by functions. What about measures that are not necessarily induced by functions, right? I know far less about Rupert Frank and Elliot Leib than I know about Yan and Meijun. I do know that Elliot Leib is probably better at any kind of math than anyone I've ever met. I meet people in algebra and I discover, oh, they're studying things that Elliot Leib figured out. I meet people in PDEs, oh, they're studying things that Elliot Leib figured out. It's amazing. Okay, so here is so these two theorems, right? I have kind of some regularity assumptions on f, but I only need this property to be satisfied. I can classify the measure. If I give up the regularity assumption on f, but then trade it for this, then I can classify the measure. So this is amazing to me because a priori mu could have point masses or lower dimensional, like maybe like some submanifold where it's supported, right? Or points where it's supported. It doesn't have to be induced by a function. You're not assuming that. But somehow miraculously, it still has to be induced by a bubble. This is amazing to me. So anyway, this is the classification theorem that I wanted to get to, right? There are very few measures that do this. Only the ones induced by bubbles, right? Pretty cool. So why do we care? I wanted to maybe take a few minutes, roughly 10, to discuss how this is used in PDEs, right? So
Application.
yeah, exactly.
Mathews, why did this bubble become important suddenly? It just came out of the sky in your discussion.
It did just come out of the sky. That's exactly right. If I was going to give you a quick reason for why this is called a bubble.
No, the functional form of it, 1 over 1 plus
and where
x
did it
squared.
come from?
Yeah.
And why is it called a bubble? If you take the sphere Sn, not Sn minus 1, and stereographically project down to Rn, the the two Riemannian metrics, there's one on Rn, like the standard one, and then one inherited from Sn. They are conformally equivalent, and the conformal factor is of this form. That's why it's called a bubble. Because the sphere looks like a bubble, right? Yeah.
And it also means that those two assumptions are pretty restrictive.
Did that answer your question? It comes from kind of imposing the spherical geometry on Euclidean space.
So the suggestion is that that's the only possibility.
That's the only possibility, yeah.
Well, suggestion that
There's a theory.
theorem.
theorem.
Yeah, that's what. Okay, yeah.
Yeah. Okay, so long story short, if I have a PDE, say, it doesn't have to be a PDE, it could be an integral equation that enjoys these symmetries in the sense that if I have a solution to this thing, and that solution, and then if how can I say? Let's do an example. Isn't that terrifying?
Yes.
Let me look at just. This is what I mean by the Laplacian, right? So this thing, let me write down the symmetries of this guy. This thing has a logarithmic inversion symmetry. So so U is a solution. I don't know how to write this. Then so is, let me call it LS of U. So this is what I want to write here is theta S, but I'll show you like why that's not the case. So this thing, this is still the inversion of X, right? But usually I have a factor out front, like theta S of U should have a factor out front. But here the factor is additive and logarithmic, right? But if I did e to the u, then this thing would end up multiplicative, right? So let me call this the logarithmic inversion, right? So if I have a solution to this, then no matter how I choose x0, no matter how I choose lambda, this guy is also a solution. So if you have equations with this kind of symmetry, this is going to tell you exactly what the solutions look like, right? So the game for this is recognize the symmetry, first of all, and now you know that this is in play. How can I, from this PDE and this integral condition, kind of squeeze out enough information to show that these things are satisfied, right? Once I do that, I know exactly what the solutions look like, right? So typically when you write these kinds of papers, it's like 30 pages of showing that these things are both satisfied. And then like half of a page of applying this and yeah. So yeah.
Is the idea to find one solution and then you have millions of
No,
solutions?
no. The idea, so let me show you, how do you, from the PDE, right, from this information, how would I detect, given x0, how do I detect a lambda for which this happens, right? From the PDE. So I'm not gonna like do the computation, I'm just kind of waving my hands.
Before you proceed, Matthew, is it possible that that could be negative 1/1 minus x squared? That doesn't,
Where?
in that bubble? Is it 1/1 minus magnitude of x?
Oh, you want minus here?
Yeah, is that allowed?
That would probably be like hyperbolic, some kind of hyperbolic stereographic projection. I would say, I don't know for sure, but if it works out, I bet this is like a hyperbolic geometry thing, not a spherical geometry.
Just with the analogy with the metric for the
Yeah.
universe,
Yeah.
just by analogy.
But I never looked
Okay,
into it.
okay.
Yeah. More questions? Okay. So how do you detect, right? So basically what you need to do from this,
From Maxwell equations.
you
Yeah,
need
just-
to show. Let me draw you, so I'm gonna draw you a picture, right? So this is you. You don't really know what you looks like, right? Because all you have is the PDE, right? For every x0, so for all x0, there exists lambda positive such that if I look at, so let's draw a small ball of radius small lambda. So this should be the picture here, right? So this is. Let's do this to e to the u. So the point is, if lambda is small, then the original function dominates its inversion outside of the ball of radius lambda. Right, so there exists lambda such that inversion of e to the u dominates let me say, is dominated by e to the u outside of ball of center x0 radius sigma whenever sigma is small, right? So if lambda is small, this is the picture. The function itself, like outside of this ball, the function itself dominates his inversion, right? So this is the starting point. Now you want to take the soup of the lambdas that have this property, right? So and so what you imagine is as I make this ball like wider and wider, here is like the intermediate point of the cartoon, right? So let me try to draw x0 right below. So this would be like this magic value lambda x0, where the inversion and the function itself totally agree. Right? And now I have this inversion symmetry, right? So in the case of the original bubble, if this were the original bubble, this lambda x0 would have happened to be this thing, right? If lambda is smaller than that, then this is the picture, right? The inversion dominates inside the ball, but is dominated outside of the ball, right? So this is why it's called moving spheres, right? I take a small sphere and I'm like moving it. This method is called the moving sphere method. And I'm making it larger and larger until I have that inversion symmetry, right? I think that's all I want to say. So I guess maybe I should tell you, maybe that's not all I want to say. Briefly, this is imposing that e to the u induces a finite measure, right? So that's kind of telling you that when I apply this, I should apply it to e to the u, even though u itself has, or the equation has this logarithmic kind of thing. But if I exponentiate it, it becomes like the traditional inversion symmetry, right? So what this, at the end of the day, right? E to the U is a bubble, right? Typically this is n, but we're in n equals 2 dimensions. I think I put that on r squared. Yes. So now I know every solution looks like that. Right? I need to logarithmic, take the log on both sides, and now I have u, right? Okay, again, this is like 30 pages. So, yeah, so I won't do it. Okay, I think that's it. That's really it this time.
All right. I have a comment to Rajesh's question. So you see here x minus z, right? This is the x minus z squared. This is a norm squared. So in Minkowski space, then the metric has pluses and minuses. And this is where these pluses and minuses will be mixed. Actually, both of them will show up if you want to apply it to Maxwell equations.
Yeah.
So the minus might show up, yes, but then it needs to be, you know,
Yeah,
over no. So the norm, you don't put this minus outside. The norm itself has pluses and minuses.
Oh, yeah, because this is, yeah, this thing you mean,
Yes, exactly.
yeah.
This is
It's not a
exactly-
sum of squares, right? It has
No,
like
this is
maybe signature n minus 1
Exactly.
and then minus 1.
Yeah,
And then a single minus 1, n minus 1.
the
plus
one
this.
in that case is the time and the other one is the space, at least if
Yeah,
I again by
Yeah,
analogy.
right.
And the exponential of u that you're saying, that's common
But
in the.
I think
metric.
when you do that, right? This is the negative part of the signature, and this is maybe the positive part. I don't know, is my guess.
No, I think just this contributes both of them, just the norm.
Right, but I'm saying after changing the notation, like this might be the positive part of the signature, and that might be the negative part. It's like 1 over the distance squared or something like that. But some of the negatives are in there. Anyway, I shouldn't say too much because like I said, I don't know a lot about it.
okay. If n is even, it won't matter, right?
Yeah, I don't know. I would have to think about it. Not on the spot. Yeah.
Yeah, very nice. Can you tell us maybe, so you're using it in your research for?
Yeah.
what?
So if you want to, so what's the long story short, right? Why are people concerned about this, right? Say in R2. So from a geometric perspective, what does this thing mean? So you think of k of x as a prescribed curvature function. So at point x, the curvature of the metric if u is a solution, right? This metric at x has curvature k of x. Right, so k is a function, and I'm trying to assign at every point of Rn a curvature. I'm imposing a geometry, right? And so if I find a solution to this, then I have a metric with that geometry. Long story short, if I want to understand the solutions to this, I need to understand the solutions to this. Because what happens is that solutions to this kind of become out of control, unbounded in some sense, and you need to understand how exactly do they come unbounded. And the way they come unbounded is by this dilation here, that as R, right? These things get kind of taller and skinnier. So it's kind of understanding kind of how all of the unboundedness of solutions could possibly happen here is encoded here. This is kind of long story short. It's a huge like analytical obstacle to overcome to solve these kinds of things, right? And this understanding the basic solutions to this thing is the first step. Does that answer your question?
Yeah, sure.
Yeah,
No,
okay.
right.
Okay.
So
I'm really interested in bubble stone.
Yeah.
From a soap